Alarms scream through the tunnel boring machine as milky slurry sprays from a failing joint. Seawater punches through with the weight of 70 meters of ocean above, and crews scramble with emergency grout while voices clash. One shouting to increase face pressure, another warning it'll rupture the remaining seals. 10 seconds to decide between catastrophe and collapse. This is China's $40 billion gamble. The Bohai Strait tunnel, stretching 123 kilometers under some of the world's most treacherous seabed. Active earthquake faults slice through waterlogged sediments that want to flow like soup, while political deadlines tick toward an impossible finish date. Is this engineering's next great triumph, or will it become the most expensive monument to overreach ever built? The route connects Dalian to Yantai, where winter ice locks ferries in port, and cargo worth billions sits stranded, waiting for a crossing that may never come.
The Bohai Strait doesn't want this tunnel to exist, and it's got the geology to prove it. Picture the seabed. Not solid rock, but a chaotic layer cake of quaternary sediments dumped by ancient rivers and grinding glaciers. Buried valleys snake through the route like hidden trenches, filled with loose sand and clay that acts more like pressurized mud than stable ground. When a tunnel boring machine pushes through this mess, every grain becomes a potential escape route for the sea above. The real nightmare lives in the pore pressure. In normal soil, water sits quietly between particles. Here, it's trapped under tremendous pressure, turning stable sediment into a time bomb. Hit a high-pressure zone wrong, and you don't get a controlled leak. You get a blowout that can flood the tunnel face in minutes. The ground literally liquefies and flows toward any opening it can find. Now layer on the seismic reality. The Tanlu fault zone cuts directly through eastern China, while the Haiyuan system lurks to the west. These aren't ancient, sleeping giants. They're active systems that regularly generate magnitude 6 to 7 earthquakes. A major quake doesn't need to hit the tunnel directly to cause disaster. It just needs to shake the segmented tunnel lining hard enough to shift joints by a few millimeters, creating pathways for water infiltration that grow wider with every tidal cycle. What makes this worse are the methane pockets scattered throughout the seabed like buried landmines. Ancient organic matter decomposed under pressure, creating gas-charged layers that can kick like a spring when disturbed. Breach one of these pockets, and suddenly you're not just fighting water, you're fighting a pressurized mixture of gas, water, and fine sediments that can overwhelm even the most sophisticated tunnel boring machine. The engineering team studied every underwater tunnel disaster in history, and the lessons are sobering. Japan's Seikan Tunnel battled massive water inflows and lost workers to flooding during construction. That tunnel was shorter, in more stable geology, yet still took decades to complete and cost far more than projected. The Bohai route is longer, deeper, and runs through ground that makes Seikan's challenges look manageable. Early planning considered an immersed tube approach, essentially sinking prefabricated tunnel sections to the seabed and connecting them. But the Bohai Strait's fierce currents, winter ice sheets that move like bulldozers, and heavy shipping traffic make surface operations nearly impossible for months each year. The deep bore option became the only viable choice, even though it multiplies the exposure to geological hazards. The pressure mathematics are relentless. Every 10 meters of depth adds roughly 1 atmosphere of pressure to the tunnel structure. At the planned depth of 70 to 100 meters below the seabed, gaskets and joints endure constant stress that combines with micro-movements from tides, thermal expansion, and seismic activity. Materials that seem bulletproof in laboratory testing face decades of this grinding, never-ending assault. The ground conditions change without warning. Tunnel boring machines designed for consistent rock suddenly encounter loose sand, then glacial cobbles, then soft clay, sometimes within a single day's advance. These transitions torture the equipment, crack seals at the worst possible moments, and create maintenance nightmares in an environment where every repair requires working under pressure with the ocean pressing down from above. The answer to impossible geology isn't hope. It's engineering that assumes the worst and builds for it anyway. The tunnel boring machines heading into the Bohai Strait aren't standard equipment. These are hybrid monsters, 15 to 17 meters in diameter, designed to change personality mid-drive. In stable clay, they operate as earth pressure balance machines, using the excavated soil itself to counterbalance the water pressure trying to flood in. But when sensors detect water-charged sand or loose sediments ahead, they instantly transform into slurry machines, flooding their cutting chambers with pressurized bentonite fluid to match the external pressure pound for pound. This switching capability isn't a luxury, it's survival. The cutter head alone generates enough torque to twist a skyscraper, with disc cutters that get swapped out through pressurized airlocks while the machine keeps boring. Maintenance crews enter hyperbaric chambers, work under crushing pressure, and replace worn cutting tools without ever stopping the advance. Stop for too long and the face can collapse or flood. The real innovation lives in the tunnel lining itself. Forget everything you know about rigid concrete tubes. These segments are designed to move, flex, and sacrifice themselves to save the overall structure. Each ring consists of reinforced concrete segments locked together like vertebrae, but with a crucial difference. They're built to fail in controlled ways. The gasket system alone represents a revolution in waterproofing. Double seals run around every segment joint, made from hydrophilic materials that actually swell when they contact water. This creates a self-healing barrier that gets stronger as it gets wetter. Behind these primary seals, secondary gaskets provide backup protection, and if both fail, the segments themselves are designed with sacrificial zones that crack in predetermined patterns to relieve pressure rather than catastrophically fail. Around known fault zones, the design gets even more radical. Shear keys, interlocking concrete profiles, resist lateral movement, while crushable layers act like automotive crumple zones, absorbing seismic energy that would otherwise shatter rigid joints. Special bellows joints installed at regular intervals allow millimeters of movement in any direction, turning potentially destructive earthquake motion into manageable flexing. The waterproofing strategy operates on multiple defensive layers. First, the gasketed segments themselves. Second, a grouted annulus, the space between the tunnel lining and the excavated rock, filled with specialized cement mixes designed to resist washout from tidal currents. Third, where geology demands it, a complete secondary lining creates a pressure sandwich that can handle leaks in the primary structure. Every meter of tunnel carries a nervous system of fiber optic sensors that monitor strain, temperature, and movement in real time. Acoustic emission detectors listen for the subtle sounds of microcracking before human eyes could ever spot the damage. Thousands of data channels feed into machine learning systems trained to recognize the early warning signs of failure, the subtle pattern changes that happen hours or days before catastrophic events. The tribore layout itself becomes a safety system. Two parallel rail tunnels connected by a central service tunnel every few hundred meters means that smoke, fire, or flooding in one tube doesn't trap passengers. The middle tunnel serves as both a construction highway and an emergency escape route, with its own independent ventilation system that can pressurize to keep smoke out during evacuations. Power redundancy runs through every system. Dual electrical feeds, sectional breakers, and isolated emergency supplies ensure that a failure in one area doesn't cascade into system-wide darkness. If the main grid fails during an emergency, trains coast to designated refuge areas rather than stopping dead in potentially dangerous locations. But the most crucial element isn't hardware, it's the construction sequencing. Multiple tunnel boring machines launch simultaneously from both shores, advancing toward a precision rendezvous point under the deepest part of the strait. Meeting tolerances measured in millimeters after boring for dozens of kilometers through shifting, unpredictable ground. Miss the alignment, and months of underwater repairs await in conditions that make normal construction look simple. The engineering can survive the geology, but can the project survive the politics of a $40 billion headline? Run the earthquake scenario. A magnitude 6.5 rupture snaps along a nearby fault at 3:47 a.m. Within 3 seconds, seismic sensors throughout the tunnel spike red. Automatic train control systems slam emergency brakes. Sectional power breakers trip in affected segments, while the rest of the system stays live. The isolation joints flex as designed, gaskets compress under stress, and the tunnel lining creaks but holds, assuming every design assumption was correct. The real test isn't the shaking itself, it's what happens in the 30 minutes afterward. Operations teams flip to earthquake protocols. Trains coast to designated refuge chambers. Ventilation systems reverse to compartmentalize any smoke. Emergency crews mobilize, while engineers watch sensor feeds for the telltale signs of water infiltration. Because failure rarely announces itself with drama, it starts with a hairline crack that grows, a gasket that weeps, a joint that shifts just enough to create a pathway for the sea. Insurance markets watch these scenarios like hawks. Coverage premiums hinge on mathematical proof that sacrificial joints and flexible linings actually work under real seismic stress. If the models don't convince actuaries, policy delays can halt tunnel boring machine launches. Without insurance, financing costs multiply. Time becomes the most expensive material on the project. The procurement web creates its own vulnerabilities. State-led consortia operate under compressed schedules that incentivize subtle corner cutting. Not dramatic failures, small compromises that accumulate. Segment cure times shortened by hours. Grout testing batches skipped during busy periods. Sensor calibrations deferred to meet deadlines. Each deviation seems minor in isolation, but underwater, minor problems become major disasters. Historical precedent haunts every decision. The Channel Tunnel fires rewrote global standards for ventilation and emergency evacuation. Seikan's construction floods killed workers and forced complete redesigns of waterproofing systems. Even recent projects like Qingdao's immersed tunnel sections leaked, teaching expensive lessons about tidal cycles and joint detailing. Each failure forced safety codes to evolve, but the Bohai project faces conditions more severe than any previous underwater tunnel. The public narrative swings on a pendulum between pride and panic. Early construction progress generates national celebration and infrastructure tourism. Then the first major delay hits headlines. Sunk cost psychology kicks in. Too much invested to quit, too much risk to continue. Political deadlines harden into ultimatums that push good engineers to accept temporary compromises that become permanent vulnerabilities. Environmental lawsuits add friction at every phase. Dredging operations cloud fishing grounds. Dewatering systems alter coastal aquifers. Marine life protection groups challenge permits. Each legal pause drains calendar time and construction budgets, while interest costs compound daily. The national mandate doesn't eliminate local opposition, it just redirects it through courts and regulatory agencies. The economic calculation seems straightforward. Eliminate ferry delays, keep freight moving year-round, and the return on investment compounds across entire supply chains. But this assumes near-perfect uptime. A tunnel closed for months after a seismic event or major leak transforms from economic artery to stranded asset. The margin between triumph and disaster lives in those reliability percentages. Then comes the stress test that matters most. Not from earthquakes or water, but from the first emergency drill footage that leaks to social media. Smoke evacuation takes longer than promised. Emergency lighting fails in sections. Critics call it theater over substance. Audits follow. Contractors renegotiate terms. The project survives not by avoiding scrutiny, but by inviting it and proving the systems work when lives depend on them. This tunnel represents either humanity's next leap in deep-sea engineering or the most expensive lesson in overreach ever built into the seabed. The stakes extend far beyond China. Every coastal nation watches to see if the impossible can become routine. Subscribe for more engineering at the edge of human capability.